Hi friends, good morning. Welcome back to another session in the problems and design of tension members from steel structures. Today we'll try to wind up this chapter with the last two problems. Later on, further in the next sessions, we'll start new topic, that is design of compression members. Okay, so today we'll try to solve two more design problems which are very important for your essay type questions in your external or internal examinations. Okay, right. Design, I'm writing the question. Design a single angle tension member, single angle tension member for a roof truss, okay, to carry a factored tensile force of 300 kilonewtons. Check for block shear. Is not necessary. Take Fi as 250 Newton per mm square and Fu as 410 Newton per mm square. Length of weld is 150 mm. So this is the given question. So if you observe if you compare this question with the previous questions, in that only axial loads were given and they have not mentioned specially that check for block shear is not required like that. But in this question, if I take the given data here, they have mentioned clearly factored tensile force. Okay, means it is PU. Factored tensile force is PU, which is 300 kilonewtons. Next, Fy 250 Newton per mm square. Next, Fu 410 Newton per mm square. Next, length of weld is given as 150. Okay. Next, they have specially mentioned that check for block shear. That is what TDB is not required. Not required. This is the question mentioned. Okay. So, based upon this given data, we will be assuming the permissible tensile stress. Assuming permissible tensile stress. What is that? It is denoted by FTD, which is equals to 0.9 times of Fi. So 0.9 into 250, you will be coming across 225 Newton per mm square. Okay. Now, gross area required equals to what? Area required equals to PU by what? FTD, which is PU is how much given? 300 kilonewtons. If I multiply with 10 power 3, it will becomes 2 newtons and it is 225. Okay. Now if I solve this one, 300 into e power 3 divided by, so how much I am getting? 33.33 mm square. Now increase the area by 10%. So how much it will be? 1.10 into 1333.33 into 1.10. Okay, so you are getting around how much? 1466.66 mm square. Okay, now based upon the given data, based upon the area required, I am choosing the section. So angle section, and they have not at all mentioned whether to take equal angle section or unequal angle section. Okay, this is, so I am going for take the angle section. Okay, so here in the index page you will be having, right, rolled steel beams, rolled steel channels, rolled steel equal angle, rolled steel unequal angle, like that. We'll be go checking unequal angle. You can go for equal angle also. You try for those problems. I am telling you unequal. Okay, you can go for equal angles also, right? So this is beams, channels, channel, angle sections, equal. You try with the same area in the equal angles. I am going to tell you, explain you unequal angle sections. Okay, so as I said you earlier, the design problem will be varying with the person to person, right? Now what I have to check? I have to check in the areas. These are the areas. Now how much I got? 1466.6 means 14.66 and above you have to see. So here in this line it is not there. Okay, and here it is nearby 14, it is not overall available. So next after 14 we are having directly this 15.51, right, means 1551, so which is very near to our thing, right? What I am doing now, choose ISA 100 by 65 by 10 mm. Okay, from SP6, we call what? SP6 or steel table. Okay, choose what you have to choose? ISA 100 by 65 by 10 mm with an area of how much? 1551 mm square. This is the area. Next, what you are required with? Anything else from this one? Nothing else, right? So based upon that one, first we'll try to calculate design strength due to yielding of cross section. Design strength due to yielding of cross section. Okay, so for that, what is the formula? TDG equals to AG Fi by gamma m0. This is the formula I have obtained. Now what is AG? What we are taking is this one, 1551 into Fy is 250 divided by gamma m0 for yielding, it is 1.10. Okay, so 1551 into 250 divided by 1.10. So how much you are getting? 352.500 kilonewtons. This is the value you obtained under strength due to yielding. Okay, next second one is, what is the definition? Strength due to rupture of critical section. I think it has been completed. Design strength due to rupture of critical section. So it is denoted by what? TDN, which is equals to 0.9 ANCFU by gamma M1 plus beta AGO Fy by gamma M0. Very easy to remember, right? Now what is that one? ANC, connected leg area. Always when you are taking unequal angle section, prefer to connect with the longer leg for the strength purpose. Prefer to connect with the longer leg. So what is the longer leg length? 100 minus thickness by 2 into thickness. So it will be 10 by 2 means 5, 900 minus 5 means 95 into 10 means 950 mm square. Okay. Next, AGO, outstanding leg. What is this? 65 minus, okay, 10 by 2 into 10. Okay. So 10 by 2 means 5, 65 minus 5 means 60 into 10 means 600 mm square. Now beta. What is beta? 1.4 minus 0.076 into W by T, okay, into Fy by Fu, okay, into Bs by Lc, right? Now what is 1.4 minus 0.076? W is one outstanding leg, 65, thickness is 10, 250 by what is Fy given? 410 into what is BS? What is BS? Same 65 for single angle, and it is 150 given. If I solve this one, 65 divided by 100, sorry, 150, I'm sorry, 250 by 410 into 65 by 10 into 1.4 minus answer. So I am getting 1.26. Now we have to check whether it is in between or not. Beta minimum is 0.7. What is beta max? Fu gamma M0 by Fy gamma M1. 410 by 1.10 divided by 250 by 1.25, if I am correct. Okay, so 410 into 1.10 divided by 250, so I am getting 1.443. 1.443 means we got 1.26, which is greater than 0.7 and less than 1.44, right? Now everything I got, I will substitute in this one. So TDN equals to what? 0.9. What is ANC? You got 950 into 410 divided by 1.25 plus beta is 1.26 into outstanding leg, how much it is? 600 into 250 divided by 1.10. Okay, 0.9 into 950 into 410 divided by 1.25. Okay, so 280.440 kilonewtons plus 1.26 into 600 into 250 divided by 1.10. 1 second. 1.26 into 600 into 250 divided by 1.10. So 171.818 kilonewton. Total you will be getting how much? 280.440 plus 171.818. That is 452.258 what? Kilonewtons. Now out of these two, the design tensile strength of section chosen is lesser of what? TDG and TDN, lesser of TDG and TDN. How much you are getting? This is 352 and this is 452. So 352.500 kilonewton. Okay, this is the value which is greater than the given factor load. How much? 300 kilonewtons. Okay, so this is the, hence our section chosen is safe. And since they have not at all mentioned any length, effective length, so that it is not possible to calculate the maximum slenderness ratio value, the slenderness ratio value to compare with the maximum slenderness ratio value. Okay, so next we'll do the design problem on double angle section connected on either side of gusset plate. So next, second problem, design, okay, a double angle tension member connected, okay, on each side of gusset plate, each side of a 10 mm thick gusset plate, 10 mm thick gusset plate, to carry an axial factored load of 375 kilonewtons. Again they have mentioned the factored. Length of weld is 300 mm. Take Fy as 250 Newton per mm square and Fu as 410 Newton per mm square. So this is the given data. Question. This is the question given. Now we'll write the given data first. Okay, it's very important. That is factored load. Factored load, it is denoted by how? Pu, which is equals to 375 kilonewtons, right? Now Fy is given as 250 Newton per mm square and Fu is given as 410 Newton per mm square and length of weld is given as 300 mm, right? Now here assume, what you have to assume, this is a design, permissible tensile stress, assume permissible tensile stress, that is denoted by FTD, which is equals to 0.9 into Fy. Okay, so 0.9 into Fy is 250, again same 225 Newton per mm square. This is the value. Okay, now area required, how much? Pu by FTD. So what is Pu? 375 kilonewtons it is, into 10 power 3 you will be getting in newtons, divided by 225. If I solve this one, 375 divided by 225, so how much you are getting? 1666.67 mm square. Now what we do, we'll increase it by 10%, increasing area by 10 to 25 you can go, so 10 is more than enough. So gross area required equals to 1.1 into 1666.67. So 1833.33 mm square. This is the area required. Now see here, this is the area required to bear this load, but they have mentioned clearly design a double angle tension member, right? So in the steel table, that is SP6, you won't have the double angle areas. You will be having only area for single angle. Now you have to choose each single angle and connect it on either side. So area, this is the total area required to bear this one. So area of each angle to be, each angle equals to 1833.33 divided by 2. So 916.66 mm square. This is the area required. Now we'll see here. So see here, 916 we required 938. So 75 by 50 by. So choose ISA 75 by 50 by what, 8 mm with an area of 938 mm square. Okay, so what will be the gross area of two angles? Two into 938, so 1876 it will be. 938 into 2, so 1876 mm square. So this is the area. Now we'll solve. Design strength due to gross section yielding. So what is the formula? TDG equals to AG Fi by gamma m naught. AG Fi by gamma m naught. So what is AG? 1876 into 250 divided by 1.10 into 250. So 426.36 kilonewtons. Next, design strength due to what? Rupture of critical section. Rupture of critical section, right? What is the formula? TDN equals to 0.9 ANC Fu by gamma M1 plus beta AGO Fi by gamma M0, right? Now ANC, connected leg length, that is 75 minus, what is the thing we have taken, 8 by 2 into 8, so 71 into 8, 568 mm square. Area of outstanding leg, so it is 50 minus 8 by 2 into 8. So 46 into 8. 368. But see here, this is the area for what? Single angles. But we are designing for what? Double angles. So into 2. Okay, don't get confused or forget at this step. So 568 into 2. How much you are getting? 1136 mm square. So next beta. 1.4, 0.076 W by T. Okay. Next Fy by Fu into B by W. See, since we are doing double angle, don't write here 2 into 2 here. Okay. These are the factor 0.076 into outstanding 50 by 8. Okay. 250 by 410 into 50 by 300. If I solve this one, so 50 by 300 into 250 by 410 into 50 by 8 into 1.35. Anyway, we have calculated in the previous problem. In that you will be getting 1.44. So if I substitute, anyway, once we'll check it. What is this one? What is beta max problem formula? Fu gamma m naught by Fy by gamma m1. Same 410 into 1.10. So it is 1.44. Okay. Now substitute here. TDN equals to 0.9 into 1136 ANC into 410 divided by 1.25 plus what is beta? 1.35 into 736 into 250 divided by 1.10. If I solve it separately, 0.9 into 1136 into 410 divided by 1.25. So 335.34 kilonewtons plus 1.35 into 736 into 250 divided by 1.10. So 225.818. So how much you are getting? 335.34 plus 225.818. Sorry. So 561.158. Okay. Next, design strength due to block shear. Design strength due to block shear. For that, what were the formulas? That is TDB1. Okay. AVG Fy by root 3 into gamma m naught plus 0.9 ATN Fu by gamma m1. This is TdB2, this is TdB1. Okay, now this is equals to 0.9 into AVN FU by root 3 gamma m1 plus ATG Fy by what? Gamma m0. This is the formula. Now you all know, earlier we have discussed that area under shear, AVG or AVN, what is that? Length of weld into 2 into thickness, but here double angle into 2. Okay, so 2 into 300 into 2 into 8 mm. How much it is? So 2 into 300 into 2 into 8. So 9600 mm square. Next, ATG or ATN, area under tension. That is what? Connected leg length into thickness. What is connected leg? 75 into thickness into 2 plates, right? Sorry, 2 angles. So 75 into 2, 8 into 2. So how much it is? 1200 mm square, right? Now after calculations I got AVG or AVN as how much? 9600 mm square. Okay, next ATG or ATN means area under shear and area under tension, 1200 mm square. Okay, right. Now what is TdB1? AVG Fy by root 3 gamma m0 plus 0.9 ATN Fu by gamma m1. If I substitute here, AVG means 9600 into 250 divided by root 3 into 1.10 plus 0.9 into 1200 into 410 divided by 1.25. So how much it is? 9600 into 250 divided by root of 3 into so how much it is? 1259.63 kilonewtons plus 0.9 into 1200 into 410 divided by 1.25. So 354.240. Altogether 1259.63 plus 354.24. So 13.87 kilonewtons, right? Next, TdB2. Okay, how much it is? 0.9 into this AVG means it is what? AVN into Fu by root 3 into gamma m1 plus ATG. Here gross average shear will come, net tension will come. Here net shear will come, gross shear will come, got tension will come, right? Gamma m0. Okay, so 0.9 into 9600 into 410 divided by root 3 into 1.25 plus what is ATG? 1200 into Fy 250 divided by 1.10. If I solve this one, 0.9 into 9600 into 410 divided by root of 3 into 1.25. So how much it is? 1636. Okay, 0.16 kilonewtons plus 1200 into 250, 1.10. How much we are getting? 272.727. Altogether 1636.16 plus 272.727. Now here, out of TDB1 and TDB2, you are supposed to take what? Least of these two. So 1630 next. Now if I try to write all those values, TDG, TDN and TDB. What is this TDG? How much it is? 426.36. 426.36. What is TDB? 561.15. 561.158. All these are what? Kilonewtons. Next one is 1613.87 kilonewtons. Now the design, okay, tensile, this statement is very much important. The design tensile strength of double angle section chosen, double angle section chosen is lesser of these three values, that is lesser of what? TDG, TDN and TDB. That is how much? 426.36 kilonewtons, which is greater than given factor tensile load, that is 375 kilonewtons. Hence our section chosen and design is safe to take the load of 375 kilonewtons and more up to 426.37 kilonewtons, right? Yeah friends, I hope with this we have completed problems. Once I will revise the whole chapter details, what we have learned in this chapter from the previous 4 plus 1 this today's 5 videos. Okay, and when the first comes to the first video, we have discussed about the introduction to tensile members. Introduction to tension members means where we are using these tension members. We have seen the applications. Okay, we have seen the applications. So if you see this, in the starting we have discussed what is a tension member and what are the applications of tension members. Okay, and what is this? This is a tension member or tie member in a roof truss. Okay, bracings and in cable suspension bridges we'll be seeing the tensile members. And to these tension members are of different tension forms, different forms, shapes. That is, we have seen a rod, a flat, a tube. Okay, single angle section, double angle section, T section, I section, multiple angle section, and channel sections placed back to back. Okay, so these are the different forms of tension members. Next, coming to here, gross area and net area. Okay, so we have seen the difference between the gross area and net area. In case of a members connected with welded joints, the gross area and net area will be same, whereas if in a members connected to the either through rivet or bolt, we'll be deducting some hole, making some hole, so that the gross area will not be same as a net area. Okay, that is net area for a well riveted or bolted joints will be equals to gross area minus area of holes. Next, we have seen what is the definition of a shear lag. What is the shear lag definition? Suppose a member is there, I am applying the load here in this edge. Okay, so when I am applying a tensile load at its edge, there will be a stress distribution developed within the member. Okay, that stress distribution and deformation in the flat near the vents where forces are applied are more than that of where forces are not applied. That is, non-uniform stress distribution is developed. That is nothing but a shear lag. Okay, right? Next, coming to the main tension members, there are three types of failures that may develop in the tension members. That is yielding of gross cross section, rupture of net critical section, and block shear failure, right? So these are the things. Based upon these only we are going to design, right? Next, coming to the maximum slenderness ratio. What is the slenderness ratio? It is defined as a ratio of effective length to least radius of gyration. Okay, so lambda effective length by minimum. So what this code suggests, IS 800 2007 suggests that there are three maximum values. Suppose a member which is always under tension, where reversal of stresses is not occurring, will have a maximum slenderness ratio value of 400. And suppose a member which is in a tension member taking tensile loads, but unfortunately some reversal of stresses may occur. Okay, if those reversal of stresses are due to wind or earthquake loads, then the maximum slenderness ratio will be of 350. Suppose if in a tension member, if tensile loads are taken by that member and reversal of stresses has been occurred, but not because of wind or earthquake load, in other loads other than wind and earthquake loads, if the reversal of stresses occurs, then the maximum slenderness ratio value is 180. These three values are very important while doing the problems, while checking the slenderness ratio value based upon the purpose of that member. Means, suppose if the member has been used as in a roof truss, okay, in a roof truss means there may be a chances of reversal of stresses that occur in the roof truss due to wind. So this value will be used, and these three values are very much important in your competitive examinations, especially for ESET examination. It is very, very important. Now, while doing the design strength of a tension member, while deciding the design strength of a particular member, how much load it will be carrying, we will be deciding based upon the three values. That is, three modes of failure that may occur. Based upon that criteria only, we are going to design the tension member. That is, design strength due to yielding of gross section, rupture strength of critical section, and block shear. Okay, out of these three, the lesser value will be given as a strength of a particular member. So for those, from the code page number 32 and 33, you will be having design strength due to yielding of gross section formulas. That is, TD is equals to AGFY by gamma m naught, and this is the formula due to rupture, and this is the formula for what? Block shear. This is the formula for block shear. While taking the block shear, see here, if a angle section is connected like this, these are the two planes. These are the plane which is called as a shear failure plane. When I drag like this, it will be dragging, and this will be perpendicular. Load perpendicular to this end is nothing but a tension failure plane, and parallel to this one is nothing but shear failure plane. Okay, so based upon these three formulas, we have solved number of problems. This is a problem where you can expect for 3 marks. Next, further, what we have done, we have seen problems, 3 marks problems. Okay, next, these are the 3 marks problems. Next, analysis problems. Single angle section connected. So for analysis, we have done due to cross section yielding, net section rupture, and block shear we have done. Okay, next, we have seen the difference between what is an analysis problem and a design problem. Once again I will clearly explain you regarding this one. Analysis means section details will be given. Based upon the section details you are going to calculate the TDG, TDN and TDB. Lesser value will be given as the tensile strength of that particular section. Analysis means, design means what? Load will be given. Based upon that load you have to make it factored load. Assume the FTD value, permissible design stress value. So based upon that you will be getting area. Increase the area by 10 to 25% and you will be getting the gross area required. From the SP6 chart or steel table you are going to choose the section. Based upon choosing the section you are going to determine. Okay, now here this is the design tensile strength. One more analysis problem. These are all analysis problems. Okay, up to here it is analysis problem only. Next, see here, these are the design steps for a tension member. Designing a problem. Now what is this one? Area required. First you have to do, take the load. If it is a factored load, go for second step. If it is not a factored load, make it 1.5, multiply it 1.5, you will be getting the factored load. Next you have to assuming the permissible tensile stress in the unit, that is FTD, which is equals to 0.9 times of F5. So based upon that one, area required equals to PU by FTD, right? PU by FTD you will be getting some area. Increase the area by 10 to 25%. So in general 10% is more than enough. Okay, so from steel table or SP6 you have to choose the section. After choosing the section, whatever the things you have done in analysis problem, the same. Means you have to determine the design strength due to TG, gross section yielding, rupture of critical section and block shear, so that you will be getting. Now after getting the value you obtained here, that value should be more than the factored load you have taken. If it is okay, then our design is safe. Okay, so these are the design problems we have seen. Okay, so these are the design problems, and this is one T section problem which we have done. Okay, and design problem you are supposed to check the slenderness ratio also, even if they are given with some values. Okay, so single angle design we have done, right? Next this is single angle design. Next today we have done the double angle problem. I hope you understood this chapter completely. Tomorrow we'll try to start a new chapter, that is design of compression members. Thank you for watching my video.